2.10, example 7. Yeah. Hey, we discovered yesterday graphically that the derivative of the natural log of x was the positive branch of 1 over x. Yeah? And then we reviewed the transformation where you take the absolute value of the input, the x, and we got the natural log of the absolute value of x, which reflected our purple graph across the y-axis and gave us y-axis symmetry. And we discovered graphically that its derivative was also the same, 1 over x, but we were now able to use both branches of 1 over x, so we expanded the domain. That's not really a proof, unfortunately, when you do things graphically, but it is an indication of what might be. To prove it, we need to actually do some analytics, and that's what we're doing on example 7. It says, if f of x equals the natural log of the absolute value of x, which I broke it into the piecewise function for you. I probably should not have done that. Use your result to prove what the derivative of the natural log of x is. Okay, so let's see why this piecewise function works. We have the absolute value around the x. So if x happens to already be a positive number, how do you take the absolute value of a positive number? You don't. You just take it as is, right? However, if it's a negative input, how do you manually make a negative number positive? You multiply it by -1. Now notice I have it to the left of 0 and to the right of 0, but I don't have it defined at 0. Why? What's the natural log of 0? Doesn't exist. Okay. So now that we have a piecewise derivative, I can take a piecewise function, I can take a piecewise derivative. Let's do the top piece first. What's the derivative of the natural log of x? 1 over x. We actually derived that yesterday, so we know that's legit. And on the bottom, we got the natural log of the blob. It's a chain rule, right? What's the derivative of the natural log of the blob? 1 over the blob times the chain rule, the derivative of the blob. What's the derivative of negative x? -1. And that's good everywhere to the left of 0. Now look what we have there. If I simplify, that's, of course, 1 over x to the right of 0. But what happens with your negatives here in the bottom part? They divide out, and we're left with 1 over x to the left of 0. Sweet! So we don't need a piecewise function anymore, do we? We can just say f prime of x equals 1 over x. And we don't even have to say for x not equal 0 because the domain is preserved. It's implied. So there you go. We got it. That's pretty neat. So if you haven't memorized it already, and I think you did, the derivative of the natural log of x is 1 over x. But the domain for this one only works to the right of 0 because that's the domain of the function we're starting with. This one here, the domain or the derivative of the natural log of the absolute value of x is also 1 over x. But now it works for all negative values of x as well. That's pretty cool. The absolute values just go away. And of course, there's the chain rule. 1 over u times u prime. We use that in the warm-up. If you want to remember u prime over u, that's fine. If you just want to think 1 over u times the derivative of u, that works as well. All right, so we're going to try it out. Simplify early and often. We said this is our new mantra. Now we add the especially when you have logs to the end of that. All right, part A. We have h of x equals cosine of blob. You walk up to the problem, it's a cosine rule, yeah? So this will be a chain rule. H prime of x is, let's see, what's the derivative of cosine of blob? Negative sine of the blob. And now you look inside that big box and you have a smaller box and you're like, oh, it's the natural log of x. Good thing I know how to take its derivative. What's the derivative of the natural log of x? 1 over x. And we're done unpacking boxes. That was easy. A lot easier than helping someone move a couch. Help them unpack boxes. So if you want to, you could just tidy it up just a smidgen, right? Put it over x. All right, so in that case, our new natural log rule was inside. It was part of a larger chain rule. Letter B. Whoa. Y equals the natural log of 1 plus natural log of x. There's 2 natural logs there. Inch by inch, it's a cinch, right? Work from the outside in. We got natural log of blob. So y prime would be 1 over the blob being 1 plus the natural log of x, yeah? And then times, we go inside, and we have 2 terms. Parentheses, very important if you think your derivative is going to be more than 1 term. I like to just have them anyway. Better to have them and not need them than to need them and not have them. What's the derivative of 1? 0. I'm going to write it down for inventory purposes. Plus the derivative of the natural log of x? 1 over x. Yeah. Now, of course, we can simplify, and we don't really need the 0 there, so we're just multiplying. And you could say it's x times the quantity, 1 plus ln of x, or you could distribute. That's probably going to be the answer that you'd see. But again, just playing around with some of the other options, distributing gives you x ln of x. And not that this would be the case, but what could happen with the x coefficient now of the natural log of x? Yeah, it would come up as the natural log of x to the x. I don't think that would be the answer, because the purpose of logs is to make something like x to the x, which is really big, make it smaller. That's what logs are designed to do. Make uncomfortably large or incredibly small numbers manageable. So either one of these maybe is the final answer on a multiple choice. All right, how about this one? F of u equals the natural log of the square root of 3u plus 2 over 3u minus 2. Whoa, f of u is right. Because if I try to go to f prime of u, that's going to be the natural log of blob. That's 1 over the blob. Ugh. Times the derivative of the blob, which is going to be some ugly chain rule, right? 1/2 blob to the negative 1/2. Oh, yuck. Notice that I'm complaining, but I'm doing it while I'm complaining. That's the difference between just complaining. Times, yuck, gross, the ho-de-hi rule. Ho, de-hi. Okay, I give up. That's gross. That's gross. I think I could continue and finish it, but maybe there's a smarter way. And of course there is, because we're simplifying early and often, and now, especially when we have logs. The properties of logs, as we've already seen, can make life easier. So let's just rewrite f of u as the natural log of all of that to the 1/2 power, right? And of course, then what could I do with the 1/2? I could bring it up front. And now I have a quotient, which, notice that already, just that one little thing makes it easier, because now I don't have that extra chain rule in there. But I can still go further, right? Because now I have a quotient, natural log of a quotient, and that turns into the what of the logs? Sum or difference? Difference. Now here's where you need to be careful, because you need parentheses there, because you're going to generate two terms. So it's the natural log of the top minus the natural log of the bottom. And if you would prefer at this point, you could distribute the 1/2 to each of them, but I'm not going to. Oh, wow, that makes it so much nicer. Actually, I think I will distribute the 1/2. Not that you would have to, because you can just leave it out in front of both of them. But sometimes it's better to distribute and just think of it as two separate terms. So now I have two terms instead of one big term. It's twice the work, but it's not really, right? Even though it's more terms, because each term now is super easy. Now let's go to f prime. Don't stop right there, because you haven't BOTC'd yet. Now we got f prime of u. And in the first term, the 1/2 goes along for the ride. And now we just have the natural log of blob. What's the derivative of the natural log of blob? 1 over blob times the derivative of the blob, which is 3. So here's where you can go u prime over u, blob prime over blob. You could say it's 3 over 3u plus 2. That saves a little bit of writing. That's the chain rule built in, because there's always a 1 in the top from the natural log rule. So 1/2 equals, and if you say it's the natural log of the blob, it could be blob prime over blob, or u prime over u. If not 1 over u times the derivative of u. Either way, that was easy. That's a lot nicer looking derivative. It's easier to work with, so I would probably do that on my own accord if I had to use the derivative for something. It's probably also what the multiple choice answers would resemble. So look for opportunities to simplify prior to differentiating, especially when you have what? Logs, yeah. From there, you can even do a couple of things. You could get a common denominator. It looks like we're going to have conjugates with the 3u plus 2 and 3u minus 2, so you could expand it back out if you wanted to, but I'm going to stop right there. Okay, so let's move on to something else here. What if What if we're taking the logs of things that are not base e? Like if I ask you for the derivative with respect of log base 2. We know how to do it with exponentials, right? Let's review that. The derivative with respect to x of base b to the x, if it's not base e, of course, it's itself. And we did what? Times the natural log of the base. That was that vertical dilation factor. So there ought to be something equivalent for logs that are not base e, right? Natural logs, like log base 2 or even log base 10. Well, there is. And we're going to do it using the change of base formula. So we're going to derive the rule. It's always fun to kind of derive the rules so that you can see where they came from. You also have a way to reinvent them if you ever forget them. Yeah? If y equals log base b of x, use the change of base formula to find the derivative. Well, the change of base formula, if you remember, did I write it? No. Let's go ahead and review it. If y equals log base b of x, you can pick any base you want. I'm going to call it a. And you can rewrite log base b of x as log base a of x over log base a of the old base. It works for any base, a. Choose your favorite number. You have log base 7, you want to turn to log base 3? No problem. Let's try it. You have log base 7 of x, and you want to convert it to log base 3? Well, that's log base 3 of x over log base 3 of 7. Works. Now, I don't know why 3 is your favorite base. You know what my favorite base is? Huh? 33. It's close. 13. Yeah, I imagine that. Yeah, that would be Larry Bird's favorite base. Yeah. No, actually, my favorite base is not 13. I lied. I'm sorry. I was feeling guilty. I was debating whether I should confess or not. What? Home? Home base. Oh, home base. My favorite base is home. Home plate. Home base. No, they call it home plate, not home base. Yeah, home plate. No, my favorite base is E. Guess what your favorite base should be in this class, at least? E, right. If you're in science class, your favorite base is probably 10. So let's go ahead and derive the derivative then, getting back to the task at hand, for log base b. We're going to rewrite that as the natural log of x over the natural log of b. That's using the change of base formula, converting it to base e. Now remember, because b is a number, right? It's a number that's between 0 and 1 or greater than 1. Log of b is now a number, or the natural log of b is also a number. So what I can do is I can rewrite that as 1 over the natural log of b times the natural log of x, yes? And now I have a constant multiple times the natural log of x. And this is something that I know how to find the derivative of. Constant multiples go along for the ride. So I get 1 over the natural log of b times the derivative of the natural log of x, which all day long is what? 1 over x. And there you go. We've just come up with a way to take the derivative of any log that's not base b. It's going to be 1 over x, just like it would be if it were just natural log of x. But if it's not base e, instead of multiplying by the natural log of base, like we do for exponentials, we end up doing what? Dividing by the natural log of the base, because it's a log. And how are exponentials and logs related? Inverses. And what's the inverse operation of multiplication? Division. Coinky-dink? Nah, it's not. Okay, so any log of any base, 1 over the blob, 1 over the argument, chain rule still in the house, but then you divide by the natural log of the base, or you multiply by the natural log of the base in the denominator, not the numerator, however you want to think about it. All right, so now we got to memorize that. Well, we already have it memorized, right? Because we learned it in context. We saw where it came from. There's really no memorization needed. We just have to remember it. Is that the same? I don't know. What do you think happens if we put the absolute value around the x if the base is not e? Same thing. Yeah, same thing as it would be for the natural log. 1 over the blob, 1 over the argument, and then times the natural log of base in the denominator. Here's the chain rule built right in. If it's log base b of u, it's 1 over u natural log of b, and then times u prime, which could just nestle right up there into the numerator. So, just like the natural log, u prime over u, but don't forget natural log of the base in the denominator. Ready? Here we go. If f of x equals log base 3 of 5 minus x to the 4th quantity squared, find f prime of x. Wow. This one is already written kind of in a nice form for us to differentiate, isn't it? We walk up and we first see blob squared. Blob squared. The next layer inside is log base 3 of blob, and then the innermost blob is 5 minus x to the 4th. So this will be a chain rule with how many factors? As many factors as we have layers, so I see 3, right. You got the squared layer, the log layer, and then the polynomial layer. Right. Practice, practice, practice. Where do you go to practice, Mr. Miller? The worksheet. Right. And they're portable. You could actually do them anywhere, including in France. All right, so here we go. Blob squared becomes 2 blob to the first. I'm just going to rewrite the inner blob. Right. You don't take the derivative of that layer at that moment. Times the next layer is log base 3 of blob. Totally got that. Log base 3 of blob is going to be 1 over the blob times the derivative of the blob, which will be negative 4x cubed. But then don't forget to do what? Natural log of the base. Somewhere in the denominator there's a factor. So instead of doing u prime over u, I just did the chain rule. 1 over the blob, natural log of the base, and then off to the side times the derivative of 5 minus x to the 4th, which feel free to put it in the numerator right away. And then the innermost blob, the derivative of 5 minus x to the 4th. I already did that, didn't I? Yeah, I already did that. Yeah, notice if you think of that chain rule built into the log rule, you've already taken care of that inner layer, so you don't want to do it again. Okay? And that's it. You want to try and clean it up? Yeah, I don't want to try either. I want to be successful, so let's just do it. F prime of x equals, let's see, I got a 2 times the negative 4. That's going to be a negative 8x cubed log base 3 of 5 minus x to the 4th all over 5 minus x to the 4th natural log of 3. Now we could distribute the natural log of 3 in the denominator, right? And then I could bring the 5 up and call it 3 cubed. Probably not a good idea. What else could we do to make this look uglier? Could I bring the whole negative 8x cubed and bring it up as an exponent on that? Yeah, do you think we're going to? No, let's not and say we did. Yeah, okay, cool. Inch by inch, it's a cinch, right? Layer by layer, it's layer. Layer by layer, we become a problem slayer. I like that. Good, teamwork. Factor by factor, we're not a slacker. Factor by factor, factor by factor, we become correct problem enactors. Oh, yeah. I am trying too hard now. Yeah. All right. Hey. You remember up here on f of u? Remember how we were saying f of u to begin with? Because that was the function's name. That's the only reason we were saying that. Right. It was sure nice to have that log there. Because we were able to take advantage of the properties of logs to rewrite it into something that was so manageable it was almost enjoyable to manage it, right? But it was all incumbent upon that natural log being there. Agreed? If that natural log had been absent, then we probably would not have been able to use the log properties to rewrite it, right? We would have had to have just used brute force and hit it with the sledgehammer, and we probably could have been successful. But thank goodness it was there, right? Thank goodness. Let's just appreciate it one more time. I don't know. Let's see. If it were not there, yeah, I don't know. Does that work? Well, apparently I can't undo it. But if it weren't there, could I just add it in? Is that what you mean? I don't know. Oh, yeah, maybe. Yeah. Hey, I think that'd be great. Like, let's look at this one right here. Like on example 11. It says find derivative of each of the following. We got y equals that. Oh my gosh. I'm going to rename this one f of u. I'm going to rename this one capital F of u. No, I can't name it f of u. I'd have to change all the variables. I would just call it f of x. Or let's just leave it as y. Anything to keep us from having to start doing this, right? I don't even want to begin. Because to take the derivative, I walk up, I see it's going to be the Ho-D-Hi rule, right? That's not a big deal, Ho-D-Hi. I got the Ho part down, right? Ho, and then D-Hi. Yikes. D-Hi is now a product rule with a chain rule. That's just D-Hi. And then I got minus Hi, and then D-Ho. That looks like it's even worse, right? Product rule with the chain rule. And then over Ho looks like it's going to be easy. But the Ho-D-Hi minus Hi-D-Ho, the D parts, ugh. Unfortunately, there's not a log in front of there, right? But if there were a log in front of there, because I have an expression that has multiple factors, man, that log would take those 4 factors and turn them into 4 what? Were you waiting for me to say factor again? You knew that I would elicit like a response after the word factor, or you were just going to like interject, like we're going to factor that. Yeah. The natural log will turn the 4 factors into 4 terms. Starts with T. It'll turn it into 4 terms, and we can go term by term down the line. That's easier. But what else would it do? It would turn in all of these exponents, the 4, the x, the 1/2, and the 2. It would turn them into coefficients, which wouldn't be the chain rule anymore. It would maybe be the product rule, or maybe just the constant multiple rule. Boy, that'd be nice. That'd be nice if there were a natural log there. But Mr. Erickson, there is no log there. No, there is no log there. I don't see one there, right? I don't see one there. So maybe we can just click our Crocs together 3 times. Careful not to slip out of them when you do that. And then wait for it to magically appear. Come on, clutch, come on. Huh? If you say tractor 3 times real fast. Tractor, tractor, tractor. Ah, it worked. It worked. Yeah, you can actually take the natural log of both sides. Now, you got to be careful, because if you take the natural log of both sides, remember, we are after dy dx, right? What we've done is we have made the problem now an implicit problem. It's no longer explicitly solved for y. It's implicitly solved for y. But do we know how to do implicit differentiation? We do. Okay. So why would it be, one more time, advantageous to take the natural log of both sides in this case? Because our expression is nasty looking. It's got lots of factors and lots of exponents. And we know logs are perfectly suited for dealing with those things. So let's go ahead and expand it now. We got natural log of y. We've changed the left side. So we got the natural log of y now equals. I'm going to expand it one fell swoop. And you're all going to go do it with me, right? Every factor gets its own natural log. If it's in the numerator, it's a plus sign term. If it's a factor in the denominator, it gets a minus sign term, yeah? And then where do the exponents go? Out front. So the first factor is e to the x. It becomes the natural log of e to the x, which the x comes out front. Plus, the next factor is the natural log of x squared plus 2 to the 4th. The 4th can come out front of that term. There's the numerator. The denominator minus the natural log of x plus 1. The exponent is what? It's the square root of blob cubed, so that's to the 3 halves power. 1/2 and then cubed to the 1/2 would be 3 halves. So no, I love the participation. Minus 3 halves. Minus 3 halves. And again, that's doing 2 things in one. That's combining the square root with the cubed. And then the other factor in the bottom would be minus the natural log of x squared plus 3. And now its exponent 2 slides out front. So that's expanding it in one line, which I would encourage you to do so. Now it's pretty easy. We take the derivative of both sides with respect to x. And here's what I'm going to do. I'm going to allow you to kind of cheat again, like I took the natural log up there, because I realize it's a lot of writing. if you want to just sneak the ddx right there and sneak the ddx right there, it's okay. We could still follow the work if you do that. Kind of remodel it a little bit to save a little bit of writing. Now, what becomes of the left side? The derivative of the natural log of blob is 1 over the blob times the derivative of the blob, which is dy dx. Yeah. And now we just go down the line. What's the derivative of x natural log of e? 1, because the natural log of e is 1, right? And the derivative of x becomes 1. Plus 4 goes along for the ride. The derivative of the natural log of blob is 1 over blob. So 1 over x squared plus 2 times the derivative of x squared plus 2, which is 2x. So are you okay with the way I did that? Blob prime over blob. A little bit faster, a little bit tidier. Minus 3 halves. We're going to have the derivative of, or 1 over the blob, so it's 1 over x plus 1, times the derivative of x plus 1, which happens to be 1. And then the last term, 2 goes along for the ride. 1 over blob times the derivative of the blob in the numerator. And there's the right side. Now, it's real easy to lose sight of what it is we're trying to accomplish. We're trying to find what? dy dx. Is it solved for dy dx yet? No. All we have to do to solve for dy dx is multiply both sides by y. So as I do that, I'll put the beefy brackets just because there's so much to contain. And I'll also simplify, if I can, each term as I go. So I can multiply the numerator together to get 8x. The top I can get a 3. I'm going to choose not to distribute my constants into the bottom, but you certainly may. The last term becomes minus 4x over x squared plus 3. Now here's the thing. Instead of multiplying both sides by y, which will work, you'll divide it out on the left and you end up with a y on the right. Here's the thing. We made our problem an implicit equation, right? It started off explicitly as a function of y in terms of x. We don't want our derivative then to be a function of both x and y because it started as an explicit equation. So what's the last step we should probably do? Do we know what y is in terms of x? Yeah, it's that original expression. So that's the last little step. Just rewrite that whole thing. And now you have it back in terms of a function of x. And remember, rewriting is not difficult. It's a little bit tedious. Just take your time. Make sure you get everything copied correctly. I'm guilty of going too fast and being careless. There it is. And that's a nice way to get the derivative. It sure beats the alternative, right, of not having the logs there. Notice we did take the log of both sides to do that, but in the end, did our answer have any logs in it? They all went away, yeah. Notice the characteristic look. Whenever you take the natural log of both sides of something that's bulky, that's the whole reason we took the natural log, the last step is going to be multiplying back through by y, which is the original function. So most of the time, the method that we used here is going to have the original function as a factor on the outside of something that has usually multiple terms. It could be just one term, but usually there's 2 terms or more, and then times that big old bulky thing. So it has a very characteristic look. Why do I bring that to your attention? If this showed up as a multiple choice answer, you may be able to eliminate some of the answer choices and look for the one that has that original function as a factored out thing. Now, there ought to be a name for this method, so we just don't have to call it that method of taking the log of both sides when you have something that's characteristically bulky with a lot of factors and exponents. That's a long name. We could probably list that out and get acronym by taking the first letter of each word in that long sentence, but that itself would also be very long. So you know what we call it? We call it logarithmic differentiation. Logarithmic differentiation. That's still pretty long, right? So once you practice enough that you've mastered it, then welcome to the log diff club. We're just going to call it log diff. But you don't get the patch until you've mastered it. Don't say you've mastered it and call it log diff because we'll know. Log diff. What is log diff then? Log diff is simply the process of taking the natural log of both sides to help you take the derivative of something that is characteristically ugly. All right, so you can use the properties of logs to turn, again, factors into terms or exponents into constant multiples. when does log diff work? It actually works all the time. When do you have to use log diff? Did we have to use log diff on this one? No. You had the option, and it was well to your advantage to do so. There's only a couple times where you have to use log diff. You have to use log diff when the instructions, of course, say use logarithmic differentiation too, blah, blah, blah. But there's another time where you have to. Whenever you have a hybrid function that is a combination exponential and power function, that is when you have a variable base and a variable exponent. It's not purely a power rule, and it's not purely an exponential. It's a hybrid. You have to use log diff, and the instructions aren't going to say to do so. But you're welcome to use it anytime. You're welcome to use it anytime you want. All right, let's go ahead and look at example B. Notice it's the verb format. It's not the noun format. It says take the derivative with respect to x of sine of x raised to the cosine of x power. Is that going to be a sine rule? Is it going to be a cosine rule? Is it going to be an exponential rule? You have a function of x raised to a function of x power. That is one of your hybrids, right? It's not a power rule, it's not a sine rule, and it's not purely exponential. You have a variable in the base and the exponent. Guess what method is required? It's required that you use log diff, right? There are all kinds of correct wrong answers, and I'm not even going to go through some of them. But there's only one correct answer. Now, in the verb format, you have a little bit more work to show because log diff requires that you take the natural log of what? Both sides of an equation. You can't just take the natural log of an expression because you change its value. But on an equation, you can do that. So the first thing that you want to do, if it's in the verb format and you're using log diff, is just go ahead and call the expression you're differentiating y. It's that easy. And of course, now you're after dy dx. If you can get dy dx, you have the derivative of the right side. Once you have it equal to dy dx, now you can take the natural log of both sides. So you get the natural log of y equals the natural log of sine of x. And what happens with the cosine of x now that the log's there? It slides out front, so you can do that in one step. So what did taking the log of both sides do? It turned a hybrid problem, a variable raised to a variable power, into a what rule? A product rule. It is an implicit equation now, but no big deal. We know how to take the derivative implicitly, but now we have a product rule over there. So the next step would be to take the derivative of both sides with respect to x. This one's not that long, so I'll just go ahead and rewrite it again. And here, when you rewrite it, this is a good time to kind of tidy things up or add grouping symbols to help you take the derivative. And I need to start working a little bit more to the right, or since we're done with this, we'll put it in a space bag and store it under the bed. All right, good. What do I do next? What's the derivative of the left side? The derivative of the natural log of y is? Well, yeah, dy dx over y, or 1 over y times dy dx. 1 over the blob times the derivative of the blob with respect to x. And on the right side, I got the product rule. So I'll do the first one first. That's how I do it. The derivative of cosine is sine of x times the second, the natural log of sine of x. It is negative sine of x. Thank you. That felt wrong. Negative sine of x. And then I have regular old cosine of x times the derivative of the natural log of blob. So now the second factor is going to require the chain rule. So the derivative of the natural log of blob is 1 over the blob times the derivative of the blob. What's the derivative of sine? Cosine. Oh my gosh, the derivative of the natural log of sine of x is cosine over sine, also known as cotangent. That's good to know. I wonder what the antiderivative of cotangent is, if there is such a thing. Okay, just thinking ahead. Let's go ahead and finish the problem up here. Solving for dy dx is the last step, and don't forget it. So on the left side, I've got negative sine of x times the natural log of sine of x. And then over here, there's a couple ways you could simplify that second term, right? You can call it cosine squared over sine, or you can call it cosine times cotangent. I'm going to be more into the cosine times cotangent things just so I don't have to generate a denominator. And then, of course, all of that times y. Now, here's definitely where we don't want to just leave it as y because we introduced y into the problem ourselves. Not that it was given and it was explicitly solved for y, but y was just a temporary variable that we used to take the derivative. We're after dy dx, so instead of putting a y here, I'm going to put what y is equal to, which is sine of x raised to the cosine of x power. And there's your answer. Your answer is what's on the right side, sorry. And notice again it has that characteristic look. The expression in this case that we are differentiating ends up being a factor right here on the outside. And then it's multiplied by something that has more than one term. So you might be able to pick him out of a lineup. They had a bunch of answer choices there. All right, now that was required to use log diff.
Teachers, please pardon this interruption. At this time, please take out that QR code that was placed in your teacher boxes and allow your seniors to vote for their prom theme.
Okay.
If you have mixed classes, please make sure that only seniors are casting their votes. The voting will only be open today from 11:25 to 11:40. So seniors, today will be your only time to cast your vote for your prom theme. Thank you.
Okay, I'm going to work one more example, and then we have time still. Okay, this one doesn't take that long. We'll just squeeze in example 12, and then we'll do the prom theme thing. Okay. So one last thing before we start. It was required on part B, log diff, because we had a variable raised to a variable power, right? And we wanted its derivative. That turns it into a product. It was well worth it to use log diff on the first one because it had lots of factors / lots of exponents. It wasn't required, but it was really helpful to have it. Of course, if the directions ever say to use it, use it. But I want to show you that it does work all the time. So if you just really get into log diff, like some people get into Disney trading pins, then you can use log diff, or Disney pin trading, I should say. You can use log diff every time. So let's go ahead and use log diff here. What's the answer? What is y prime, by the way, before we even start? 2x. So you have the answer. But if you want to use log diff because it's more fun and it kind of draws out the problem so you could savor it more, I get that. Let's take the natural log of both sides. We get the natural log of y equals the natural log of x squared. All right, now I can bring the 2 in front. Oh, yeah, getting rid of that exponent, that tedious, cumbersome exponent. Now it's a constant multiple. Goes along for the ride. Now I'll take the derivative of both sides with respect to x, and I'll go ahead and show that. And here we go. Here's the calculus step. It's ephemeral. It doesn't last very long. The derivative of the left side is 1 over y times y prime. Is it okay to use y prime? Sure. And on the right, 2 goes along for the ride, times the derivative of the natural log of x is 1 over x. And now all we have to do is solve for y prime, and we get 2 over x times y. Well, all I got to do now is substitute y back in. What was y equal to? X squared. So if I substitute that, I get 2x squared over x. And, of course, what happens with one of those x's? They divide out, leaving us with 2x, which we know is the derivative of x squared by the power rule. So when does log diff work? Yes, one?
So if we were given any couple function we wanted to differentiate, we can just use log diff.
You can use log diff every time, right? Yeah, yeah. Sometimes it creates more work for yourself, but sometimes work is just comforting in and of itself, right? It's soothing, it's relaxing. If you forget how to do the power rule, right, you can use that. You say, like, I only have the natural log rule at my disposal, right? Okay, yeah, well, log diff always works. It may take a little bit longer, but it will work. Hey, speaking of running out of time, we need to get y'all to vote for y'all senior themes. So we'll stop there today, and we'll pick up right where we left off tomorrow.